Welcome. Thanks for coming here despite being the last day before spring break and Dragon Day. In fact, the reason I got delayed is because I got stuck behind a gigantic dragon. All right, please put your laptops away, close your laptops. Okay, so we talked yesterday about, or Wednesday, about kernelization. And the idea is we have these linear classifiers that we understand really well. And we like them a lot because they have these convex optimization problems, and we just initialize our loss with some weight vector, and we just do gradient descent. It's super easy. And outcomes solution is very, very fast. So everything about them is nice, except one problem. They have really high bias. Right? So linear classifiers suffer from high bias. And, oh, mic is off? Wait, no, that's on. One, two, test better? Okay, good. So linear classifiers suffer from high bias. And the question is, how can we fix this? And so the first idea we had was, well, what we do is when we have high bias, one option is just to add more features. So one thing we could do is we could just take the existing features and add combinations of these features to artificially inflate our dimensionality. And that works really well. The downside of this is that it increases your dimensionality of your vector, and it becomes very slow. But then I showed you one thing, is that we can actually write this vector W, at least for the square loss, we can write it as alpha I xi. So we can write this vector W as a linear combination of these x's. And the beauty of this is that, or if we actually, in this, let's say we try to do this transformation phi of x, then we would have these phi of x here. And the beauty of it is that we actually never have to compute this vector W. Instead, we just have to store these n values alpha. So the beauty is that now our vector W is independent of the dimensionality of our feature space. So we can project our data to an extremely high feature space, and we can still learn it because we just have to keep track of n alphas, no matter what the dimensionality is. So that's the first thing. The second thing is then we realize that if we do a square loss, and it's true for other losses as well, in fact for all the losses that we talked about, is that the inputs are only accessed in terms of inner products. So we only ever compute phi of xi transpose phi of xj. That's the only way we access these xi's and xj's. And so the beautiful thing is that we don't actually ever have to take our data and map it into a high dimensional space. Instead, it's sufficient to define an inner product function that computes us this inner product term. And that's all we need to do. And very often, this is much, much, much easier, exponentially easier and faster than actually mapping the data in a high dimensional space and then computing inner products. Right? So if you have, like in many cases, you can compute this inner product extremely efficiently. And that's what we call our kernel function. That's why we call it K. Any questions about last lecture? Yeah?
So kernel functions have to be non-negative everywhere, correct?
No. Right, so the simplest one is a simple counterexample. The linear kernel, x and z, is just x transpose c. Well, this can clearly be negative.
So what are the limitations you have to have?
It has to be positive semi-definite. So if you take n data points and compute a matrix K such that Kij equals K of xi xj, this matrix has to be positive semi-definite. That's the constraint. So you can have negative inner products. Any more questions? So in some sense, what the inner product measures is if larger means they're more similar, and lower means they're less similar. Right? So that's typically 0 means orthogonal. Okay, good. So this is a great question you just asked, because this is exactly where I want to go today. I want to teach you how to construct new kernels. And basically, let's kind of demystify these kernels a little bit. So talked about last time, we have the linear kernel. This is this one. This is a pretty famous one. This is basically, if you just use that linear kernel, then you get exactly the same result as if you would use a linear classifier. This is, you didn't change anything. You may still sometimes use a kernel function. Can anyone tell me why? Why would it be efficient? Why would it be a good idea to run your algorithm in the kernelized fashion? Under what setting is this advantageous? Yeah? That's right, that's exactly right. If D is larger than N, right? So if computing these inner products is very, very costly because we have, in this case, phi is just the identity, but vectors are really, really high dimensional, but I don't have many of them. So I could just pre-compute this kernel matrix K, right, and then actually just run everything in this space. So you have this, for example, with DNA data. So DNA data, typically you don't have all that much because, each data point corresponds to a human where you actually, had to sequence the entire DNA. That's very expensive, or used to be very expensive. So your N is small, but your D is ridiculously high, right? So in those cases, it makes sense to just once pay for basically computing all the pairwise inner products and then do all the learning in the inner product space. In the kernel, in the kernelized version. So the second kernel that we had is the RBF kernel. That's the cool kernel. That's what I refer to as the Brad Pitt of the kernels, right? So that's K of x, z. I don't know if Brad Pitt is still cool these days, but I guess he used to be cool. X minus z squared over sigma squared. And so the intuition here is that basically we put a Gaussian around every single data point, and we say points are similar if they are close by, and if they are far away, then we don't know anything, right? So this goes to 0 very, very quickly, right? So if they're far away, then they're basically orthogonal, right? Actually, it's mapping your data into some hypersphere, some positive quadrant of some infinite dimensional sphere. That's what you're doing. And the polynomial kernel, the polynomial kernel is this one, where we have 1 plus x transpose z to the power of p. But this is the degree, or d, whatever. This is the degree of my polynomial. So these are the most common kernels, but you can construct your own. And what I want to show you today is some rules that actually constructing your own kernels is quite simple. And it's to some degree a superpower if you know how to do this, right? So if you actually have some specific data, let's say you go into any kind of chemistry or biology, I don't know what your PhD will be, or whatever, or what your application will be, and it helps, if you can actually take some weird data and be able to construct a kernel, that can make learning very efficient without you actually having to squeeze it into some vector form. So the first, basically, I wrote down 8 rules for you for how to make kernels. There's more, but those are the most common ones. And the first one is that the linear kernel is a kernel, right? And that's very easy to prove. It's a positive semi-definite matrix because it's an inner product matrix. So that's you can just do that on a rainy day like today. K of x, z, x transpose z, that is a well-defined kernel. That's my first rule. So, and that's what we've been doing the whole time. So that's, in some sense, all I'm saying, this is a well-defined inner product. Well, duh, right? That's how, that's what an inner product is. That's the inner product you learned in high school, right? The second one is more interesting. The second one says, if I have a kernel function, k1 of x, and I multiply it by any constant that's non-negative. That's positive. And well, it can't be 0, but then you get a trivial. This is a trivial case. So if it's non-negative, this is still a well-defined kernel. Okay, so basically just rescaling all my inner products by some positive value still gives me well-defined inner products. Well, that should be that's actually, from the definition of inner products. It just follows right away. Please ask questions anytime, if anything is unclear. And there will be a bunch of quizzes today, by the way. So make sure you sit now close to someone you like, that you can work with them together. All right. Don't move away too obviously. So the second one is if you have 2 kernel functions, if you add them up, you still get a kernel. So it's closed under addition. So we have two kernel functions, k1, k2. If I just add them up, I still get a kernel. If I take any one of them and multiply them by a constant that's positive, I still get a kernel. Okay? So these are the operations. And so basically what we will do later on is we say, okay, let's construct new kernels. And what you do is you start with something that you know is a kernel, and then you basically transform it into the function that you like. 4 is, and this is a little more interesting. So if you have a function, let me just make sure I defined this correctly here. Sorry, I didn't define it here. So g has to be a polynomial function. So if we have a function k of x, if I define my kernel as g of k1 of x comma z, and I forgot to write down what g is, and I believe it has to be a polynomial function of even degree. Positive coefficient, sorry. Okay, that's right. Okay. G polynomial with positive coefficient. Okay, that's obvious, yeah. So you can basically take, square this, cube it, etc., right? Stick it into any kind of polynomial. It stays a kernel. Stays a value-dependent product. Number 5 is, I'm just going to skip this now. I can just take two inner product functions and multiply them. It still stays a kernel. 6 is an interesting one. Now it's getting a little interesting. 6 says, if I have a kernel function and I multiply it left and right, by any function. So I have f of x on the left and f of z on the right. That's still a kernel. So I basically can transform my features as long as I do the same transformation for x and z and multiply with a kernel, then that's still a kernel. 7, if I exponentiate my kernel, that's still a kernel. And finally, 8, if I take a positive semi-definite matrices. Now, actually, I asked, I'm looking at the survey right now, and I asked people, what's the worst part about the course? And one person wrote, positive semi-definite matrices. So that's pretty, I don't know, at least it's not me. So if you take any positive semi-definite matrix and multiply it, right and left from x and z, that's also a kernel. And so if that's the identity, then you fall back onto this guy. Okay, good. Any questions about these rules? Yeah?
For example, how did we construct RBF using these rules?
That's the quiz. That's exactly what I want you to do right now. So pick your favorite neighbor. I give you 4 minutes. Try to prove that the RBF kernel is a well-defined kernel.
So the problem is it doesn't get x minus z. That's the biggest problem. Yeah. 5 repeatedly using z. I don't know how to get x minus z though yet. Well, it has to be here.
Question?
So you write x minus y squared, right? Does that mean the norm of x minus y squared?
Yeah, so it's basically right, k of x comma z equals e to the minus x minus z transpose x minus z. That's the RBF kernel. Okay, who thinks he or she has figured it out? Raise your hand. Some people, a little bit. One person. Yeah, give you 1 more minute. Sorry? So yeah, sigma is real. It's not it can't be an imaginary.
But there's a minus sign, right?
Yeah.
Yeah.
All right. I think you were the first one. Do you? Everybody, be quiet, please. Everybody. Yeah. That's exactly right. So let me just, explain it one more time for those people who thought this was a little fast. So basically, you start with X transpose C is the linear kernel. That's rule number 1. That's a well-defined kernel. Then you say I multiply this by 2 sigma squared. 2 over sigma squared. That's rule number 2. That says if you multiply with a positive constant, it's still a kernel. Then I use rule number 7, where I say I can exponentiate it. That's now I have exactly the middle part. And now I can use rule number, what is it? I don't see it right now. Oh, 6, rule number 6. That says I can multiply this with f of x on the left and f of z on the right for any function f of x and f of z. And so I define them as here. Right? And then I get exactly this term on the left. So RBF kernel in a 4-step process is very simple. Is exactly a well-defined kernel. Yes, thank you very much. It's very, very nice. Yeah. Sorry? Well, the function always has to be of 2 functions. Right? So k of x comma z is defined as x transpose z. That's a well-defined kernel. If you make this x transpose x, that's not a well-defined kernel. Right? That's a different function. So don't. Yeah, any more questions? Yeah. It has to stay, if you set it to 0, then everything becomes 1. And then you have a function that maps everything to 1. Is that positive semi-definite? The all-1 matrix? No, but if you had a polynomial that just raises the inner product to 0, then it just trivially becomes 1. So then you have a kernel that is a kernel matrix that's all 1s. Right? I'm not sure that's positive indefinite. Is it? Maybe it is. I'm not sure. So we have to look into this. Yeah, it's in some sense only looks at an extreme, excludes that silly case, but it's also a useless case. Yeah.
The
Oh, I would assume it's finite. I'm not sure. To be honest, yeah, I don't know. Certainly holds that it's finite. I'm not sure about infinite. Yeah. Last question. Yeah.
For the function rule, function of x,
Yeah.
Wouldn't you map any x to like the negative identity matrix, and then z to the identity matrix, and then you would get that negative k1 would also be a kernel?
Wait. Sorry. So f of x goes to, but there's just the problem is like f of x. You can swap x and z, right? Okay, let's take this after the class. I'm sure it doesn't work, but okay. Let me do just one more example. And so, please don't look at the next part of the notes. I forgot to remove it from the notes. I put the solution up. So I will add in the proof for this when I put it online. So another kernel I want to show you that's often used is a set kernel. So let's say your data is not vectors. Your data is sets, right? You may have that in biology or in language, actually. You have a bag of words or something, right? And so you have set 1 and set 2, right? These are not vectors. And now I define a kernel as the following. I say my kernel between two different sets, set 1, set 2, is e to the cardinality of the intersection. Right? I basically say how many points do these have in common, and then exponentiate this. And that's my kernel function. And maybe spend a minute, you and your neighbor, discuss why is that a well-defined kernel. So once again, these are now sets, right? And I'm saying how many elements do they have in common, and I exponentiate that. And that is a well-defined kernel. So please discuss it with your neighbor. Don't look at the answer, it's on the next page.
Sets are drawn from a finite domain. Okay, any guesses? Any guesses how to prove that this is a well-defined kernel? For those who didn't look at the answer? So it's a simple trick. You basically say, there's one more assumption actually that I didn't make clear, so in case that tripped you, I apologize. These sets must be from a finite universe. So if you want to look at the intersection, one thing you could do is you could theoretically say, well, I take each set and I write it as a gigantic vector, where every dimension corresponds to one possible element that has. So you basically say, well, Si maps to xi, where xi is a long binary vector, and for every single dimension you just say, so the 1 if I have that element in there, and the 0 if I don't have it in it. And then this here is identical to saying This is e to the xi transpose xj, right? And now you just have the first rule and the exponentiation rule. So the important thing is this may not be computable, this may be totally infeasible. Just the fact that it's possible in principle makes it, proves that this here is a well-defined kernel, right? So it may be easy to look up that actually, what the intersection between two sets is. Yeah, question?
Why does it have to necessarily be finite? There are infinite sets with well-defined intersections.
That may be right. It's just for this thing here. Not so. If you have an infinite dimensional vector, you have two infinite dimensional vectors. You have to show that this inner product is finite. So then you kind of get into weird exceptions. Yeah. So bag of words, essentially, you could view it as something like this. Yeah. So bag of words are basically these. There you could actually represent these vectors because they're typically very sparse. Okay, good. So in some sense, I just want to give you a flavor of how to do these proofs, and typically always sneak one onto the exam at the end. But it's also, it's not just, it's really a good thing to know, because if you can write a well-defined kernel function, right, there's a massive machinery in machine learning that just takes as input a kernel function, right? So if you can come up with a kernel function, that's basically the key to a whole world of algorithms that you could apply to your data sets. So keep that in mind, and please remember how to do this. But you have to be able to show that it's a well-defined kernel function. Otherwise, horrible things happen. Okay, any more questions? And by horrible things, I mean the loss will become negative. So that's as horrible as it gets. Okay, good. So what I want to do in the remaining time is show how to take algorithms and kernelize them. So yes, question?
Yeah, so how do you evaluate if your kernel is good for your data set?
Well, larger values should mean 2 points are similar. So you as a data expert can basically, that's something you could verify. Right? So data points that are very dissimilar should have small inner products. Data points that are similar should have large inner products. All right. So here's we call these kernel machines. So in order to take a machine learning algorithm and turn it into a kernel machine or kernelize it, we need to follow a two-step process. The first step is we take this algorithm and we have to prove that data is only accessed in terms of inner products. And that also during testing time, all you ever need is inner products. So that's the first thing. That's what we did last time. That's actually all you need to do. Like if you look at old papers, people try to prove all these representative theorems and so on. People, ultimately, all that is not necessary. There's a very pragmatic test. Just show that everything is accessed in terms of inner products. And then define a kernel function and just substitute that in terms of inner products. So the first thing is you take your algorithm, you rewrite it in terms of inner products, and then you look whenever there's an inner product, you just swap in the kernel functions, the kernel function, and that's all you need to do. So we have another quiz number 1. Here's quiz number 1B. Maybe spend a few minutes and try to kernelize the nearest neighbor algorithm. So the nearest neighbor algorithm, the L2 distance. So we try to find the nearest neighbor with the L2 distance, and then assign that label. Can you kernelize it? So please, you and your neighbor, discuss it. I'll give you 3 minutes. Oh, do you need the rules? No, you don't need the rules. So, yeah, the rules are on the notes. Okay. Yeah. All right, so who figured it out? All right. Everybody please be quiet. Yeah. Yeah. Actually, you can use any kernel. You can use any kernel, right? So the important part is you just say, well, all we need for the nearest neighbor classifier is to find the nearest points according to the Euclidean distance. The Euclidean distance is this here. You take the square root of this, actually, right? So let me just write this. This here is the Euclidean distance. But whatever is closest based on the Euclidean distance is also closed based on the squared Euclidean distance, right? So I can just take this and both sides and square them. That doesn't change anything, right? So if I take the squared Euclidean distance, I still find exactly the same nearest neighbors. And if I use the squared Euclidean distance, this here becomes x transpose x minus 2x transpose z plus z transpose z, right? And hallelujah, right? Inner product, inner product, inner product, right? So the entire algorithm accesses our data only through inner products. So what we can do is we just stick in the kernel functions here, and we say this is k of x comma x minus 2k of x comma z plus k of z comma z. And you can use any kernel you want, right? Any well-defined kernel works with this. This is now kernel nearest neighbors, right? Nobody ever uses kernel nearest neighbors. It's not a very good algorithm, and I can explain to you later on why. It doesn't make any sense. But it's, it's just a very simple example how to kernelize it. But there's other algorithms where it makes, and the reason actually it doesn't make much sense is because it's already a nonlinear algorithm. So bias is not a problem of nearest neighbor, right? It's not a high bias algorithm. So kernelizing reduces bias. We don't have a bias problem here. K-nearest neighbor suffers from a variance problem. But linear classifiers, they suffer from a bias problem. Yes? That doesn't matter. Like, we're not constructing a kernel function. When we kernelize an algorithm, all you need to show is that every single access to a data point is in an inner product. That's what you need to do, right? These rules were only to construct your own kernel function, right? So now you can stick in your own k, your favorite k function. Yeah? Yeah?
So the nearby points should have a high kernel value. And
that's right.
it depends on how we use the k.
No, but yeah, so RBF kernel you would have this, right? So the largest it gets is 1. So you would have 1, 1 here, right? And so here depends how close they are. If they are far away, then this becomes small, etc. Yeah. Okay, good. Let me go to another algorithm. So the kernel regression. And kernel regression is actually a very useful algorithm. It's very, very handy. And the beautiful thing is, it's one line of Julia. It's also one line of Python, probably. Okay, so the idea is the following. We just have the square loss, so we minimize W transpose xi minus yi squared, 1 over n. Let's just drop the 1 over n just to make it simple. This is the loss we're trying to minimize. Last lecture, we already showed that accesses data only in terms of inner product. If we make the following substitution, W equals I equals 1 to n, alpha I xi. And we showed you that that's totally valid. We can do this, right? So if you write our W this way, then everything just becomes in terms of inner products. Today I just want to derive this from the closed form solution. So if you remember, when we talked about ordinary least squares, we said that actually has a closed form solution. So this is actually a quadratic problem. It's a parabola. And the parabola has a nice function. We can just compute the minimum right away. So essentially we take 1 Newton step. And the closed form solution for ordinary least squares is W equals XX transpose inverse XY, where X is the matrix defined as all the, we basically have all the inputs kind of stacked in a row. It's like basically the way your projects work. And Y is all your y's here, I think, transpose. Yeah. Okay, so the beauty of ridge regression and ordinary least squares is that you can compute it with one line of code. That's just this line. You know, so basically just take your input, you just compute the covariance matrix, you take the inverse, multiply it by your data and by the label, and bam, this is your W. Now we would like to kernelize this. The problem is that this W here with the RBF kernel would be infinite dimensional, right? So something seems to be wrong. We can't do this, right? But the good thing is, well, we know it's going to work because we showed it last time. But one thing we can do is we can basically substitute for W this term here, right? So we take this definition of W. If you write this in matrix notation, this means we take every x, every column here, and multiply by, one alpha value, right? So basically what this means is W equals x times some vector alpha, right? So that's exactly the same thing as this, all right? So we take this vector alpha and multiply every single column here and sum it up, right? So these two are equivalent. So, and that's our W. So what we can do is we can just plug that in. We can just say x times alpha equals this thing on the right, right? This has to be correct. And now we want to solve for alpha, and hopefully what we will get is an expression that only corresponds to inner product, so we can sneak in our kernel function. So currently, not everything in terms of inner products, but we can do a cute little trick, and that's we multiply both sides by x transpose x inverse times x transpose. So we multiply by this, x transpose x inverse times x transpose. And why are we doing this? Because now this here basically dissolves, right? These two evaporate. And we have to do this here on the right side too. Now this gets a little ugly. Sorry, one sec. Sorry, this becomes x transpose x inverse times x transpose, and now we have here x transpose inverse, oh my gosh, x, y. And so now I already told you this here, these two basically disappear if I do this trick. And here on the right hand side, what I get this terms here. X transpose, xx transpose inverse x. Let's just look at this. X transpose, xx transpose inverse x. I claim that's the identity. Right? It must be. Why is this? Well, it's quite simple. I can just multiply with x on both sides. If I multiply with x here and with here, then these here disappear and I get x equals x. Okay? So this here must be the identity. So this here disappears. This here all disappears. And the only thing that's left is alpha equals x transpose x inverse times y. And we're done. Why are we done? What's x transpose x? That's the inner product matrix of x. So that's exactly a kernel, right? So that's basically every single entry of that matrix. That's the matrix K, where Kij is Kij equals xi transpose xj. That's exactly this. So basically what we get is alpha equals the inverse kernel times y. And that's all there is to it. So then in MATLAB, if you want to solve this in MATLAB or in Julia, here's the code. Y equals k backslash y, I believe. So that's how you solve this. So it's literally one line of code. And the beautiful thing is, now if you do prediction, right, you just have your alphas, you just multiply your original data with it. And it's a super, super efficient algorithm. It's extremely powerful. Any questions? Yeah? Ah, good. Someone got me. So when I multiply with all these terms here, I made some assumption that actually this here is actually invertible, right? That actually inner product matrix is invertible. And that's exactly right. And when it's not, basically what you do is you add a little bit of a ridge. So what you do is you say the following. Alpha equals k plus sigma times identity inverse times y. And that's exactly kernelized ridge regression. That's exactly right. Very nice point. Yeah? That was just to save ink. Yes, sorry. Yeah, no, there should be an inverse. Okay, thank you very much. Actually, these notes are actually written by students who transcribe lectures. It was very nice of them. But sometimes there are little typos that I didn't catch. All right, good. So let me just walk you through this one more time. Well, I know. Who wants to see it one more time? Raise your hand. Okay, good. So basically we have the closed form solution for this. I erased all my equations here. The closed form solution for this equation here is W equals x transpose x times xy. So that's exactly this term on the left. Instead of W, I write x times alpha. And then I multiply both sides from the left with x transpose x minus 1 times x. And I'm just doing this such that a lot of terms disappear, right? Because they're all inverses of each other. And so the only thing I'm left with is x transpose x, this term here. And this here actually is my kernel matrix. So all I get is alpha is the kernel matrix times y. Let me see, I have 2 more minutes. What do you do? Do you still want to do SVMs? Or would want to do SVM at the beginning of, after the spring break? Raise your hand if you want to do it now. After spring break? It's a tie! All right, let's do it after spring break.